All right, so today we're starting weathering and erosion. And while weathering and erosion might not be one of the most exciting topics that we're going to talk about, it really is, I think at least, opening the door, paving the way, whatever you want to say there, to possibly one of the more interesting parts of the semester. We get some scary titles of PowerPoints, but Test 3, which this is the beginning of, has a lot of neat sort of classic geology in it. We're pretty much past the point about learning about rocks and minerals, and we touched on volcanoes already, which started the processes. I guess in my mind, it's the processes that are more exciting than like I said, some of the background stuff. And while this is still background, what else can I say about sedimentation and stratigraphy? That doesn't get more exciting than that, right? You guys will find something to like in it, I promise. So today we're going to begin the discussion of making sediments, moving sediments, and setting sediments down. Yeah, I can just feel the excitement rippling through the room. Now, we got 3 words for that on the title screen already, 3 vocabulary words. They're not new, all right? But if during the rock cycle you didn't quite grasp what it meant, what weathering meant, or what erosion meant, you certainly will after this conversation. But first, we got to talk about what sediments are. And again, this isn't a new word for you. You've heard of sediment before. A couple different contexts, perhaps. We're going to now narrow down what it means in the realm of geology, or science in general. So sediments are fragments of pre-existing materials, all right? Pieces, parts lying around at the surface. You remember when I introduced clastic sedimentary rocks. Sedimentary rocks made of sediment, right? And there's those pieces, parts. But just like we had that one kind of weird sedimentary rock that actually grew in water, we have to point out that, oh yes, sediments can also be stuff that grows in water, or the more formal wording of that, materials that precipitate out of solution. Now again, you've been through sedimentary rocks at this point, so you know that they come in 2 flavors. You got inorganic and organic. If they grow in water, they're always inorganic, no matter what. Even if you dissolved a whole bunch of seashells and used that calcite to grow a piece of limestone, there's no, for lack of a better word, memory in that calcite that it was ever a seashell. Okay, and you couldn't prove it one way or the other anyhow if you tried. So when we talk about those kinds of sediments, they're always inorganic, no matter what. But when we're talking about the pieces, parts lying around at the surface of the earth, well, heck, that can be anything. Okay, it can be pieces of rocks or minerals that were broken down. Remember your definition of rock, right? And it could be pieces of twigs and leaves or seashells or whatever. That's that organic component. And, well, there you go. Little summary slide. In lab, we started talking about sediment sizes. It may not have made much sense to you. I'm like, sand is no longer a noun, it is a size. A pebble is a size, not a noun. It's not a thing anymore. Well, of course there's still things. But what you think of as a pebble, what you think of as sand, especially sand, can be tiny pieces, parts of a lot of different things that are roughly just sand-sized. But we just call it sand. If I didn't say it then, I'll say it now, or I'll repeat it now at any rate. If you go out into the middle of a continent, into a desert, all right, and you take a handful of that sand, it is quite possibly of entirely different material than if you're looking forward to a vacation this summer on the coast and you're going to the Outer Banks or to Myrtle Beach or to Jersey or wherever you're going, and you pick up a handful of that sand. It could be completely different stuff. Now, don't get me wrong. There may have been an ocean in the middle of the continent at some point, and what is showing up as sand right now was old rocks and seashells that were on a shoreline. But, for example, I want them to be different. All right? They're inland sand. At any rate, so we're going to have a bunch of lists this lecture. This is your first list. This one's kind of sing-songy. Boulder, cobble, pebble, sand, silt, clay. All right? Da-da-da-da-da-da, dun-dun-dun. And I kind of want you to try to remember it that way. It'll help you keep it in your mind, because I'm going to ask you on the next test, which of these lists is in order. What you got to watch out for, which is why you don't want to be struggling to remember which size goes in the middle. What you've got to watch out for is if I say an increasing or decreasing diameter. Okay, because every so often I mix it up and I change the word in the middle of the question. Increasing diameter, of course, means getting bigger. Decreasing means getting smaller. But in test stress, I doubt you forget what those mean, but I'm guessing you just remember boulder, cobble, pebble, sand, silt, clay. And if I ask you for small to big, well, you get it wrong. So read the question. I'm never going to ask you for these numbers. This is just for, life experience sort of thing. If you ever want to correct anyone, feel free. When they say, that's a pretty big pebble, well, no, technically that's a cobble. How that goes. You might see a couple words in here that you use, like gravel and good old-fashioned rock. That's a rock. We usually use rock for something about as, big as you could get in your hand. If it's smaller than that, it depends. Depends how small it is. And then somewhere arbitrarily boulder kicks in. That's a really big rock that you can't pick up, right? So you will see gravel. Your book might even have gravel in it as a grouping. It straddles the pebble to cobble range, I think. I don't think it's on the high end of sand, but I don't want to talk about those first three too much. Sand is a neat one, because sand is both bigger and smaller than you would suspect. On the big end, 2 millimeters, all right, that's right around the size of like aquarium gravel. There's that gravel word again, all right, or Nerd's candy, okay? Probably told you this during the lab. 1/16 of a millimeter, really tiny stuff, but it should still feel gritty. That's sort of our definition of sand, is something that feels gritty. And then silts and clays. You gotta love geologists mixing fractions and metric, but hey, that's us. And you might think, who the heck can notice the difference between 1/256th of a millimeter and 1/16th of a millimeter, let alone even smaller than that? Believe it or not to your fingertips, because your fingertips are too rough, being with your fingerprint and all. But on something like your tooth, all right, silt and clay, you can feel the difference. And if you were in a pinch, in a bind, you really didn't want to bring another hunk of rock back to your office or your lab or wherever, and you're taking field notes, and again, you're in a position to care whether something is a silt stone or a clay stone. Geologists would whack it with their hammer and find out if it's gritty or not. Clay is not gritty. Clay would feel like flour, super smooth. Okay, but the silt, you'd say, "Oh, God, that feels good on my teeth," because you've been out in the field for several days, you haven't had a chance to brush your teeth. So the silt would actually feel kind of good. So boulder, cobble, pebble, sand, silt, clay. I won't make you say it with me because there's only a handful of you here today, but when I have a whole class, it's kind of nice and sing-songy. We could do it in multiple part harmonies and all of that. So why all this talk of sediment? Well, of course, weathering produces sediment, and erosion, as you'll see in a couple minutes, transports sediment, okay? So weathering is the breakdown of materials at the surface of the earth by the agents of weathering. Now bear with me on that one because it seems sort of self-referential, doesn't it? Breakdown of materials at the surface of the earth by the agents of weathering. Erosion is the transportation of weathered materials at the surface of the earth by the agents of erosion. So maybe you can see where this is headed. I'm going to have to tell you, of course, about those agents here in a moment. But why would I blend them? Exactly. They do go hand in hand. In fact, they're double agents, as it were. That's what moves often breaks down. Wind, water, ice, and gravity, your second list that you need to remember. We're going to touch on these as we go through with some other stuff to talk about, but I'll just sort of introduce it now. If nothing else, it'll be redundant when we get to it officially. Wind blows and water flows, right? So the wind is blowing. Well, let's go back to our list. You got boulder, cobble, pebble, sand, silt, and clay. Which of those things can the wind blow on a normal day? Always got to put that little disclaimer. Sand and below. Good. Yeah, is it going to blow a boulder around? Hopefully not. Cobbles? Again, hopefully not. Pebble? Usually not, huh? But if you've ever been to the beach, you know darn well that sand can blow around rather easily. One of the biggest mistakes people make is getting a brand new pair of sunglasses right before they go to the beach. Because if you don't drop them 12 times in the sand, they're still going to end up sandblasted, all scratched up. Silt and clay, of course, dust. Wandering around on a dry spring or summer day and you get dust in your eye, right, as it swirls around the parking lot or whatever. Well, as those particles are flying through the air, anything they come across can get damaged, can get broken down. We've harnessed that as humans. We call it sandblasting as one of them, right? So, here's an example of that. Water. Water's a little stronger. Water's denser than air. Water can move bigger particles. Water can easily move pebbles. Think about a stream or waves going back, right? You got to have moving water, just like you had to have moving air for wind. Again, can it move a cobble? Well, it depends. But usually we say pebbles, sand, silt, and clay. We just move it up one notch. And again, you may see those as test questions. While those particles are moving around, banging into one another, they're doing damage not only to other rocks that are around there, but themselves. Think about the last time you went to a stream and picked up a rock, or to the beach and picked up a rock. There's a really good chance that rock was round and smooth, right? Really good chance. All right. Water is nature's rock tumbler. It just takes a whole lot longer than the one you can put on your shelf. Ice and gravity, we'll get to those, but also quite important. All right, so weathering is the breakdown of materials at the surface of the earth by wind, water, ice, or gravity. Erosion is the transportation of weathered materials at the surface of the earth by the agents of, by wind, water, ice, and gravity. Or, even more clearly, weathering is the production of sediment by wind, water, ice, and gravity. And erosion is the transportation of sediment by wind, water, ice, and gravity. There are two types of breakdown that can occur. And we name them pretty simply for once. We have physical. Sometimes it's called mechanical. They've been putting mechanical in parentheses for so long, I think to remind, certain people. I'm not sure those certain people we're trying to remind are still alive. But I think what it boils down to is they used to call it mechanical breakdown back in the day. But all the textbooks still do it. But we just call it simply physical and chemical weathering. And again, these definitions, bear with me a moment because I'm going to switch the slide really quickly. These definitions are very similar. The physical breakdown of rock versus the chemical breakdown of rock. Okay? We're going to show you, though, how that differs. So when you physically break down a rock, you're getting smaller pieces. Think about when you're a little kid and you're bashing one rock into another one. I always think of one of the Wile E. Coyote episodes I used to watch, where he's got a giant boulder at the top of the hill. The idea, of course, have that roadrunner stop down there and eat that bird seed. He's going to roll that giant rock down. He's going to squish a roadrunner. It's a perfect plan. Can't fail, right? Yeah, well. So, in this episode, he starts that boulder rolling down the hill, and it's bouncing and banging, and in true animation prowess, they're showing all these little particles and bits of dust as it's going down the hill. But in this episode, this time, every time it bashes into the ground, the boulder gets a little smaller. So by the time it does get down there, of course, it's a tiny little pebble, and it doesn't crush a roadrunner at all. That is physical breakdown of rock. In fact, we're going to have a vocabulary word for that. Now, that's called abrasion. Rock against rock breakdown. Not only is that what happens when you roll a boulder down a hill, but abrasion is what's responsible for that smoothing of rocks in waves and in streams. Those rocks are rolling along in the current. They're bashing into other rocks. And in your 20-some-odd years of experience, what tends to break first? Big, heavy, thick stuff or thin pieces? Yeah, thin stuff, right? So all these little sharp edges that are on the rocks, those tend to wear away first. Round out, smooth out. And in fact, this word rounding is exactly that vocabulary word. Rounding is what happens during abrasion. It says all agents are capable of this, and that reminds me when we went back to, or going back to Wile E there for a moment. If you guys don't know who Wile E. Coyote is, I urge you to look up on, say, YouTube or something like that. I'm pretty sure everyone still knows who Roadrunner and Coyote are. But nonetheless, I mean, hell, they were 30 years old when I was a kid, so. But 20 at any rate. That was gravity, okay? Coming down the hill, that's that agent. Probably back when you learned about potential energy and kinetic energy in whatever science class that was, okay? Having that elevation and then the fact that things will roll downhill, that's what gravity is. Think of landslides. So abrasion is big, okay? Abrasion is also, we talked about sandblasting a couple moments ago. If you've ever seen any of those pictures of out west, okay, speaking of Wile E. Coyote, all those amazing vistas, these weirdly shaped rocks and arches and thises and that's. Sometimes, yeah, it was shaped by water, but a lot of that is just thousands and thousands and thousands of years of sand slowly sculpting as it blows through it. It accentuates the weak spots, digs pits and holes, which then get even deeper. And I've been lucky enough to get out there a handful of times. There's some amazing art out there that Mother Nature makes. The colors are a whole nother thing, but just the shapes themselves. And I'm realizing as I say this that I've been updating my lectures over the years with pictures. This could really benefit from some pictures. So abrasion, we talked about it with gravity, we talked about it with water, and we talked about it with wind. Okay? And I haven't even pointed out the fact that as that wind is blowing and doing this damage, it's actually traveling from point A to point B. Okay, that's the erosion. That's how it's subtle with the erosion. A stream flowing is moving that rock from point A to point B. The top of the hill to the bottom of the hill with the boulder. So, it's right there. Now, frost wedging. Frost wedging, we just lived through this. Frost wedging is, because whenever you think about, when I first introduced this, and I say ice is one of the agents, I bet everybody pictured a glacier, right? And don't get me wrong, glaciers can do some damage. And if you know someone who knows about stuff like that and you're driving in a car and you're driving through a glaciated area, they might even point out that all these rocks used to be in Canada because the glacier brought them down here and so on and so forth. All right, so it's very easy to think that that's what we're talking about. But, and it can be, don't get me wrong. But what we want to focus on with ice and weathering, at any rate, is this thing called frost wedging. And frost wedging relies on the fact that the crystalline form of water takes up more space than the liquid form of water. Now, I don't know when you learned this. It may not have been until your later high school or early college days when you threw a can in the freezer to get it cold really, really quickly, and maybe because you've had too many cans before that, you forgot it was there, and it explodes and leaves that horrible mess. Or, my big thing was when I was a little kid, I don't know, I wouldn't say it was my job to fill ice cube trays, but I remember filling a lot of ice cube trays right? And not only getting it from the sink to the freezer without spilling it, but I remember that sometimes when I'd pull it back out of the freezer, that those ice cubes would be higher than the ice cube tray itself. How does that work? How does that happen? And either my dad or my mom, who knows, probably my dad, said, well, ice takes up more room than water does. Oh, okay. Or water expands when it freezes is probably what he said. I'm like, okay, neat. So you don't have to fill the ice cube trays that much to get a full ice cube out, because you can count on a little bit of expansion. Well, of course, this isn't talking about ice cubes in freezers. All right, this is talking about water in rocks in winter. And you guys know by now the earth is old. She's cracked and creviced and all of that stuff. And as you go through fall into winter, the water, be it from rain or whatever, starts to freeze at night. It gets cold. And when it freezes, it expands. What's harder to believe, I think, for most of you guys, is that it's strong enough to actually pry apart the rock just a little bit. Just a little bit. But as it changes from liquid to crystal, it does pry it apart just a little bit. And then, guess what? The next time that happens, a little bit more water can get in. And then when it freezes, it pries it apart that much more. It's like a really, really slow crowbar or pry bar. And eventually, depending on which way the cracks travel and so on and so forth, it can wedge a piece entirely loose. Now, I said we just lived through this. What the heck am I talking about? Well, I'm talking about potholes. All right? This is where potholes come from. That and, I'm going to say 3-ton snowplows. I don't actually know how much a snowplow weighs, but I know they're big and they're heavy. So what happens, again, your roads, they do their best to keep them up, okay? It's in their best interest to keep them up. But, come winter, inevitably, it's going to happen. So the same thing I just said happens. The water gets down into the cracks in the blacktop and slowly but surely wedges it along. But we've got another beast that is not of nature happening here. You got that giant truck coming down the street with that big old plow in front of it, and it nicks the corner. You ever wonder why they sometimes leave a inch or so of ice on there? It's so they don't rip up the road so much. Okay? But all you got to do is just grab just the tiniest little bit of that. And then guess what? That hole again is that much bigger. We had one down at the bottom of our street. And it just grew and grew and grew and grew. All right? Yeah, I want my roads plowed, don't get me wrong. But it's, an unfortunate effect. So that's what frost wedging is talking about here. All right, again, that's weathering. It's prying it apart. That's why it's under mechanical. Now, your book's going to talk about some other ones that I didn't. Roots, believe it or not, are strong enough. You've probably seen, if you've spent any time in the woods wandering around, a tree growing up through a rock and so on and so forth. Okay? Roots are actually strong enough, again, to very, very slowly pry a rock apart. So, a lot of ways that you can break down rocks. We just picked a couple. Now, as we said, chemical weathering is a little different. Our goal isn't necessarily to make smaller, well, it's not a goal in either case. It's not thinking about it. But the end product isn't smaller pieces. The end product is, disappearing of the rock. When you think about chemical weathering, I want you to think about two things. First and easiest one is dissolving. Water, given enough time, they say, will dissolve everything. Universal solvent. All right? And when you dissolve something, you're putting it into that, you're making a mixture, you're making a solution. Taking water and you're adding whatever it is to it. And we think we're doing this a lot in life. Kool-Aid, yeah, pretty much is. But do you ever, like with chocolate milk, notice if you leave your chocolate milk when you were a little kid, that come back with your Nesquik or whatever, it sort of is lightened out in its color and a bunch of gunk on the bottom. Well, you probably put, way too much in because you're a little kid and it's Nesquik, right? But also, a lot of that, you're just drinking it while it's still suspended, okay? And it gives it that darker color. But some of it does dissolve. But like I said, Kool-Aid, it actually dissolves into it. Coffee and tea, it's not exactly dissolving. It's a different process. You're leaching there. You're pulling some materials out of it. But literally dissolving. There's not a whole lot of things we dissolve. Salt. We'll dissolve salt. We'll dissolve some sugar here or there. But like I said, a lot of our drink mixes that we do, a lot of it is really still suspension. But I tell you to raise your hand there. And the other one, you might not have thought of this one, is oxidation. Oxidation is another form of chemical weathering. It's not a whole lot of metal cars around anymore. It's the biggest problem. When I was growing up, they still had metal bumpers, and don't get me wrong, you still see rusty fenders here and there, okay? But cars used to be a heck of a lot rustier. And it's easy to see then how oxidation, rusting is one type of oxidation, was a destructive process. There's a reason, they took all that time and all that gajillion dollars to clean the Statue of Liberty a few years back. It's not just because they didn't want it to look greenish anymore. Okay? Oxidation, tarnishing, there's another word that we use for it, is destructive. It breaks it down. You're losing your detail. If you've ever spent time going to old cemeteries, and you try to read what's in what was carved in it, okay? Especially if it's old limestone stones or marble. Marble almost dissolves as easily as limestone does. It gets really, really hard. You have to do the rubbings and try to make out what it's saying there and so on and so forth. That's chemical weathering. And acid rain does a lot. It helps that process along quite a bit. So it's not just water falling down on these guys, but especially when you go to old churchyards and big cities and so on and so forth, and acid rain tends to be a more localized sort of thing. You'll see that even more so. So we got dissolving. You could call it going into solution if you want, but we'll keep it simple and just say dissolving. And oxidation is two examples of chemical weathering. These are both tied to water. Oxidation, of course, can also be tied to air. All right. So not all agents do chemical weathering. They all seem to do physical weathering, though. Questions about chemical or physical weathering and or the agents associated with? This is, what was our question? Even just plain water will do it. It just takes longer. Just in nature, luckily we don't have a whole lot of liquids running around, But water's the big one. Just sitting in a puddle sitting on something will slowly start to break it down. I just pulled in the acid rain because it compounds the effects, and we got to throw in a thing about air pollution every so often, But yeah, no. I can't think of. Can you think of another liquid out there in the environment? Okay. I don't know what mercury would do to. I have no clue what mercury would do. But you're right, it is certainly a liquid. Saliva came to mind, but that's not, I suppose you could call saliva and stomach acids chemically weathering, but not exactly in this context. So I'll ask one of my chemistry friends about mercury if I think about it. Again, we don't luckily have that running around at the surface. That'd be kind of cool though if we did. Like a mercury flow coming down a mountain or something. That would be bad. I think at the very least we could say it would be bad. It'd be cool to watch. So yeah, just a summary slide again. Okay, so that kind of wraps up weathering, okay? We touched on erosion a little bit. As I said, some of it's going to seem like redundancy. Just think of it instead of as the positive word, and not redundancy, but reinforcement. So the wind blows, the water flows. When we're talking about erosion and ice, we do go to glaciers. And yes, they do use the incredibly fancy word of pluck for how a glacier picks up stuff. We gave you grain sizes earlier. Remember boulder, cobble, pebble, sand, silt, clay? For, what wind can do, what water can do. Glaciers have no limits. They're massive, okay? I'm just going to go to the extreme. We don't have these really too much anymore, but going back to the last ice age, they say right around here, now mind you, it was a slope, but the front of the glacier was a mile high and essentially went all the way back to the North Pole. That could move through, push through anything it wants. There's no sediment size, clast size limit on that. You can recarve valleys. They can dig out lakes. They can do anything they want to. Landslides. Landslides, we already mentioned. Again, landslides fall under gravity. All right. You have that potential energy due to position. You take away some. This is my one problem with gravity, is that it does need, again, some sort of helper. Stuff doesn't just fall. It might seem random, like all of a sudden that just fell. But something has to move, help it out, I think. Even if it's the wind blowing one pebble out of the way that happened to be holding everything else back. Or again, this is out of nature, but a big semi-truck rumbling by, shaking the earth a little bit and sets something off just a little bit. But gravity, like I said, is always, in my head, it's needed some sort of trigger, right? But, so blows, flows, plucks, and falls. Blows, flows, plucks, and falls. Alrighty then. Hot Pockets are supposed to last me all morning. I better put them away. So, all this stuff we've been talking about in the background, what was being blowed and what was being flowed, and what was being rounded, and so on and so forth, of course, are sediments. Sediments, I'll remind you one more time: boulders, cobbles, pebbles, sand, silt, and clay. Okay? If you hadn't got the point by now, weathering produces sediments. Erosion transports sediments. There's the connection. There's the point. And, oh my gosh, yes, sedimentary rocks, made of sediments. And just don't forget that little asterisk. Don't forget about the ones that grow in water. We acknowledged rounding earlier. Now we're putting it firmly in context into our discussion of sediments. You may fondly recall, or you may just recall, that you differentiated between a conglomerate and a breccia in lab. And I said, oh my, students, what is the difference? Why even bother? You don't know why we bothered, but you did know that, well, the breccia has angular pebbles in it, and the conglomerate has rounded pebbles in it. Well, now that you know that that can actually tell you something, what can it tell you? It tells you whether it's been transported. Arguably, it tells you how long it's been in the environment as that sized piece, how long it's been in the environment as a pebble, so on and so forth. We have some context for that. You still may not know why they care. And I have to agree, this is my end of geology, and I still think it's a bit of a stretch to care about that, but they do. When you get into reconstructing environments, sedimentary rocks are, well, all rocks are products of environments, but a lot of our time, because sedimentary rocks are what's at the surface in most cases, we find ourselves reconstructing the environments with the sedimentary rocks, and then you could know whether or not which agents perhaps were at play, which would help you reform the environment in your head. You'd look for other clues, so on and so forth. So, well, it seems like a subtle, silly difference. It really isn't. So we told you, you guys agreed that the thin, sharp, pointy bits would probably be the most likely parts to fall off first, break off first when you're rolling a rock around against, especially if it's banging into another rock. And that's all rounding is it's smoothing things down. If you've ever spent some time whittling with a pocket knife and a stick, you might have this idea. Okay, what's going on here? And I didn't even talk about the first bullet there. It's definitely worth pointing out that this is weathering happening during erosion. Okay? Sometimes you're just moving something from point A to point B. Not always, not even usually, arguably, but you could. But this is happening during the movement. All right, starting to get to the end. We're talking about putting that sediment down now, which of course is called deposition or a deposit, right? As erosion ends, deposition occurs. Sediments are often deposited by size. Sometimes we're really rushed when we get to the end of the semester and we go through water more quickly than I'd like. So I take a moment here just to put across that idea in case we have to rush through it later. The sorting and water is a great example. So we talked about how streams could carry pebbles, sand, silts, and clays. All right. If you wanted to somehow up the capacity on this stream here, the capability, I should say, of the stream to move a cobble, what do you think you'd have to do to it? On a normal day, it carries pebbles, sand, silts, and clays. You want to make it carry one size bigger. Faster, stronger, faster. All right. Anybody else? There's one more thing that sometimes we hear, and they're connected. Sometimes people will say that you could put more water in it too. You could make it fuller. Because you're thinking about flooding, and during a flood, you see all kinds of random stuff getting moved along. All right. And again, when we get to streams, that'll be something we'll show you the connection. But you're right on with faster. More energy, more system energy. Okay. And there is, as I said, a number of ways to make a stream faster. Anywho, so the opposite could equally be said then. All right. If we want to make a stream that usually carries pebbles, sand, silts, and clays, no longer capable of carrying pebbles, only sand, silt, and clay, what would we want to do to that stream? Make it weaker by doing what to it? Slower. Slow it down. All right. We're working with the same agent. Well, same aspect. Speed. All right. If faster lets you carry bigger things, going slower means you're not going to be able to carry as big of things. So what's the point? Well, we're talking about sorting. So what happens then is you've got all these things carrying around in the stream. It's coming down the side of a mountain. It's down into a valley. Eventually it's going to hit and level out. And as it levels out, they tend to slow down. So as it slows down, one by one, it's going to drop these sediments out of suspension. It's no longer fast enough to move pebbles. So, boom, you get a bunch of pebbles dropped. Or what you might notice on a stream is, say, a gravel bar. And as it goes a little slower, all of a sudden it really can't even support sand anymore. Boom, all the sand gets dropped out, and you get a sandbar. You even know that word. So on and so forth, until the very lastest things, silts and then clays. It's not all that's left, because if you go up far enough, you'll hit the silts and the clays. But we can't usually go up far enough. I was just headed there. Thank you. So I don't know if you guys heard what she just said. All right. This is a natural progression that you can see at a beach. Now, unfortunately, we've, mucked up most of the beaches that are out there. They have to do things like bring sand in, and of course, quite often there's a paved parking lot. It works out really nice if there's a gravel parking lot. All right. But a lot of times we pave them. So you see this same progression at the beach. You're going to see the beach. We'll start at the sand, the beachy part. If you go behind that, there should be bigger clasts, okay, bigger sediment sizes, the gravel. If you can go out far enough, you'll see that there becomes the silts and the clays. All right, and that's why we only mentioned it briefly and in passing, but when we talked about limestones and shales a little bit, I said, well, no, this is deeper water, this is shallower water. It all starts to tie in because we know where this stuff tends to get deposited. So that's sorting. It happens with wind as well, okay? Wind, as we said, sand, silt, and clay typically. When the wind dies down, the sand gets dropped out of suspension, for lack of a better word. If there is a place due to geography, topography, whatever you want to call it, where the wind always tends to blow really high and then slow down, you're going to get a buildup there. Hence the deserts in many cases. So deposition is typically a function of the speed of the erosional agent. And then by proxy, the lack of sorting also tells us something. All right, you get a landslide, a landfall. Those tend to be unsorted. Just a jumbled mess. So So you can tell that, oh, this was this kind of deposit or this was that kind of deposit. Glaciers leave both sometimes, and that you got to look at some other factors in there. But glaciers will often sort. So here's a slide again that sort of summarizes what we've been talking about. Velocities, what I call system energy, and we're going to hear more about this when we get to streams, is responsible for sorting out sediments by size. As erosion ends, deposition occurs. In other words, once you stop moving, you're deposited. You put your money in the bank. Okay? You're making a deposit. The largest size deposits first, then subsequently smaller and smaller sizes, just like we talked about. So now you got a pile of dirt. And I still say that quite purposefully every year. My old office mate used to argue with me. He says, dirt's what you sweep off of your rug. I said, I don't have a rug, I have a carpet. Grumble at me. So, you've got a pile of dirt. You have a pile of sediment. At this point, a couple things can happen, right? It can undergo consolidation, lithification. That pile of sediment can become a rock. We've already taken that fork in the road. The other direction, that dirt stays there, and life happens in it, around it, on it. Critters burrow into it. Things walk by and poop on it. Leaves fall down and break down and decay on it. It becomes enriched with nutrients. And we call that a soil then. Dirt plus nutrients, sediments plus nutrients, is soil. And that has its own chapter, its own PowerPoint. Unfortunately, in the list of things that sometimes get put by the wayside, soils is one of them. Bless you. Not always, but folks that take geology tend to take environmental science as well. You still need two sciences to get out of here. Many of you do. And I know they talk about soil, so I don't feel too horribly bad when I don't get to it. So, anyhow, we've made and transported sediment, we've set it down, and we've laid a map for what comes next. It turns into a rock, or it becomes soil. And like I said, we've already talked about one, and we probably won't talk about the other. So how does this then, as I told you guys at the beginning, how does this lead to the rest of our conversations? Well, again, believe it or not, just like there are people that cared if something was rounded or pointy, there's people who care what happens in those layers, in between those layers, how long it took to put those layers down, so on and so forth. And as I say it like that, boy, it sure doesn't sound very interesting. But I hope you'll find it a little more interesting than this conversation was, at any rate. So that's where we're going to go now. Not down either one of those roads, but we're going to kind of look back and reflect. So, and this is, like I said, it is kind of interesting because we do get to talk about things like fossils, because they get trapped in these layers. We get to talk about old environments, what the rocks actually represent. We get to talk about geologic time. So we go back and we look at how the last, couple hundred years, couple billion years have been broken up, so on and so forth. So this will take us through test 3, okay? All of this stuff. And it is one of the more difficult tests. So do try to, if you've been cruising through here so far, God bless, that's great. But just a heads up, test 3's usually a little bit more difficult for folks because there's, I don't want to say actually some thinking involved, but it is a little bit more than regurgitating vocabulary words. So, which you've been getting along with so far. So, all right, you guys. that is the end of weathering and erosion.